So why study Snell's law? Well, because refraction is everywhere. You may have seen images of a straw in a glass of water where the straw looks like it's cut off at the interface. That's refraction. The reason why glasses work to improve human vision is refraction. So the reason behind lenses is refraction. In fact, the only reason you can see is because of the physics of refraction. So refraction is everywhere that light moves through a medium. One important aspect of Snell's law is lenses. What is a lens? A lens is defined as a transparent object with two surfaces where at least one of the surfaces is curved. How does a lens work? Well, obviously a flat bit of glass does not work as a lens. You can have a look at the image here. An incident ray comes in, it's refracted at the interface, yes, but this refraction is cancelled out by the refraction of the other side of the interface, here. So there is no net bending of light. But for a lens, the refraction means the path of the light follows after leaving the object is different from when it comes in. So it's effectively bent. And you can see that in the image here. The light comes in, Snell's law is followed, but because the surfaces are curved, this results in a bending of the light. And what's interesting to note is this bending is slightly different for every parallel light ray that comes in because the angle is changing. So we can focus the light into a point. So in this course, we make what's called the thin lens approximation. When the lens has a thickness, d, that's much less than the radius of curvature of the lens. In this course we only consider thin lenses, so you don't have to worry about this too much, but just a note that this is what we're doing. You can see an example of a thin lens over here. We often draw lenses instead of drawing them as bits of glass, as just a simple line with either plus for a converging lens or a minus for a diverging lens, depending on how it bends the light. What do I mean by that? Well, here is an example of some types of thin lenses, and you can see we've drawn them here just as a line with either a plus for the converging lens, you can see here on the left, and on the right we have an example of a diverging lens, which is indicated by this negative sign here, and that spreads the light out. And now we need to define focal point and focal length. This is for light that comes in parallel to the optic axis. What do I mean by the optic axis? I mean this black line down here. So the focus point is the point to which the parallel lines converge, here on the left, or which parallel lines appear to diverge, which is shown here on the right. This is for a diverging lens. So you can trace the lines back to where they appear to have come from, and this is the focal point. We also have the focal length f, which is the distance from the lens to the focal point, and this is indicated below. Here's a lens showing the image formed in a camera and a lens forming an image in your retina. In both of these cases the image is real and inverted, and it's formed by a converging lens. With flat mirrors, as we've seen, we only get virtual images. The rays only appear to come from the image. So here's the virtual image, and here's the object and the eye. Note that the mirror reflects the light. We know the light physically can't get to the other side of the mirror because it has to bounce back. On the other hand, lenses like the converging lens in this picture does form real images. With converging lenses, we have real images. The rays we see do come from the image. So here's the object, the lens, denoted by this plus sign, so we know it's a converging lens, and this forms a real inverted image on the other side of the lens. Now, to save us having to draw ray diagrams all the time, we can have a formula that calculates some of these important distances for us. This is called the thin lens formula. The thin lens formula comes from a geometric analysis of ray tracing of the thin lens. This saves us having to draw the ray diagram and measuring each time with a ruler to find out something like the focal length of the lens or the distance from the object or something like that. So the thin lens formula is 1 over d0 plus 1 over di equals 1 over f, where f is the focal length of the lens, do is the distance of the object from the lens, and di is the distance of the image on the other side of the lens. This is indicated on the diagram here, and I'll highlight them. It's also useful to define the magnification m. M, as we've mentioned before, is the ratio of the image height compared to the height of the object, which equals di over do. Note this can be negative.